Today we are going to move on to a new chapter on a new type of sensor. So we have discussed about resistance-based sensor, where the the parameter change in the environment is captured as resistance change of the sensor. We have also discussed about capacitance-based sensor, where any physical parameter change or also chemical parameter change basically is converted into capacitance change, when either the epsilon, the permittivity changes, or when the distance between the two electrode changes, or whether the interacting area between the two electrodes or multiple electrodes change. So in this chapter, in this new chapter, we are going to discuss about inductive sensor. Inductive sensor, as the name implies, mostly use the principle or the law of inductance. Inductance law, which you have learned in semester 2 in electric circuit analysis. So it is basically also similar like capacitor. It is an energy storage element. The difference is that when capacitor store the energy as charge, as polarization of charge, inductance store the energy as magnetic field, due to the changes of the current that is flowing, spiraling or winding a magnetic core. And by changing actually the parameters, for example, how the core moves along the coil of the wire, and maybe also the induced current due to the other magnetic field, then this inductance change can be measured and will relate to the environmental change that we are measuring. For example, like displacement, rotation, linear displacement. So far that I know, mostly it is used for motion or measurement of signal in the mechanical domain. And I haven't heard or haven't read any report yet on the use of inductive sensor for chemical domain or biological domain. Maybe there is, I'm not sure yet. I'm not aware of. Okay. Based on the conversion mode, we can classify inductive sensors as two. From non-electric, how the non-conventional mode here is how the inductance or inductive sensor change the non-electrical parameters to voltage. It can be classified into two types. The first one is self-inductance sensor. Second one is differential transformer sensors. The self-inductance sensors can be further classified into two different subtypes of self-inductance sensors. The first one is what we call is variable reluctance sensor. Second one is the eddy current sensor. Each will have different applications, as we will see later. In self-inductance sensor, or the first type, the variable reluctance sensor, is this is the typical self-inductance sensor. Is this variable reluctance sensor? It consists of these three components. The first one is the coil. The coil here is the wire, that winding around the core. The core is a magnetic field itself, and an armature. So the coil and armatures are made of permeable magnetic materials, for example, like silicon steel sheet and berm alloy. So when the air gap thickness between the coil and armature change, when the air gap thickness between the coil and the armature change, that is when the core, the magnetic core material in the middle, move. So then the air gap thickness between the coil and the armature will change. This will cause reluctance in the a change in the reluctance in the magnetic circuit. And as a result, the inductance of the coil that is winding the core will also change. And this inductance change can be further converted using a secondary transducer into voltage drop change across the inductance, or as frequency change using an oscillator circuit. This is what we meant, yeah, in this figure, it is illustrated where the coil is and the armature is, and this is the coil, in the middle is the core, and we have another armature is another permanent magnetic field, yeah, also made by usually also either a permanent magnet material or an magnetic material which is wounded by uh, electrical current to make it as electromagnetic, to make it as a magnetic source. So for example here, well, this is a sensor that is used to measure the rotation of this gear wheel, the rotation per minute, the speed, the rotational speed of this gear wheel. Okay, since it has this different height profile, yeah, along the perimeter of the wheel, it means the distance of the interaction between the gear wheel and the pole piece here that is wounded by the coil will be different between the peak one and the valley, yeah, between the mountain and the valley. The valley will have more distance, yeah, so will less interaction of magnetic fields, while the peak will have more intense interaction. So this is illustrated here also. So we have the coil winding around a core, usually made from ferromagnetic material, and we have a permanent magnet here. So when this coil, when this rotor rotates, yeah, the rotor rotates, then it will create magnetic field changes in the coil. As a result, then it can be shown here, yeah, as a voltage change, oscillating voltage change. For example, if it has high speed, it is shown as this high frequency sinusoidal signal, while the low frequency sinusoidal signal indicating that the rotor rotates at slower speed. This is how it looks like, yeah, in real life, the component, typical variable reluctance pickup. The second self-conductance sensor type, so this is the variable reluctance sensor, and the second one is eddy current sensor. Faraday's law states that when a massive metal conductor is placed in a mutative magnetic field or moves in a magnetic field, cutting the magnetic lines of the magnetic field, then there will be an induced eddy electric current in that conductor, yeah, which is called as eddy current. Usually the flow also will be small circles in that conductor. So the parameters that can affect the formation of this eddy current, among others, are the resistivity of that conductor itself, the magnetic permeability between the conductor and the magnetic field source. In this case, it would be the core with wounded by the coil. The geometric shape of the metal conductor itself, geometric parameters, okay, the length and how the shape, like in the previous slide we showed with gear wheel with a valley and a mountain, for example, like that. Then also it depends on the exciting current frequency in the coil, and then the distance between the coil and the conductor. So the components in eddy current sensor is the sensor coil itself, yeah. So similar like this also, and then the tested conductor. So the measurements could be the displacement, because when, for example, the sensor is displaced moving away from the conductor, or vice versa, the conductor move away or move towards the coil, then of course the magnetic field induced eddy current in the conductor will also change. Thickness, the thickness of the conductor itself, and surface temperature. So this is how it looks like. So we have an active coil here surrounding a core. A magnetic field line will protrude from this probe, having shape like this. So the darket, which is a conductive material, will be exerted or by these magnetic lines. As you see that when the conductive material moves closer towards this active coil, there will be more of the magnetic line being captured that will hit this target. As a result, there will be more eddy current as well. So the eddy current that flows through the object will depend on this different many parameters: the distance, the current flowing through this coil as well, and many others as presented here, the geometry also. This is how an eddy current sensor look like, yeah, in real world. Then the second type, besides self-inductance sensor, the second type of inductance-based sensor is what we call as differential transformer sensor. Perhaps you have learned transformer, yeah? I'm not sure, maybe you didn't cover transformer in electrical circuit analysis semester 2, yeah, where voltage is being converted from one high voltage to another voltage, and usually this involve a kind of magnetic core, and the coil with different winding turn or different turn is surrounding the same magnetic iron. And then the magnetic field will be transformed, and then it will be converted into different voltages depending on the number of the turn. Those are the basic principle of transformer. So non-electrical variation will create a mutual inductance change. Secondary coil is connected in differential forms, which will create what we call as differential transformer sensor. So this is similar. Later we will see the circuit similar like Whetstone bridge, where we subtract the resistance, the voltage divider from one to another. Later we will see this configuration of differential transformer sensor. There is what they call a solenoid type differential transformer sensor, which consists of a primary coil, a secondary coil, and a core. So it sounds similar, maybe like a normal voltage transformer that we have in many of our electric appliances. The important principle in differential transformer sensor is the occurrence of this mutual inductance. So non-electrical variation will create mutual inductance change. This non-electrical variation can be distance change, what else? Other motion change, etc. The secondary coil is connected in differential forms, which then is called as differential transformer sensor. Something like this. We have three coils here, and we have the source coil here at the middle, A, where an alternating current is flown through. So there is a create electric magnetic field. And then on its left and on its right, there are two coils, which is basically connected. It's represented by B. Now, in the middle, there is this core, which has this blue magnetic field. Yeah. So when this core is exactly at the middle, which is at A here, then the captured magnetic field by the two transformer B left and B right will be the same. So then they will cancel each other. The subtraction will be zero. However, when the core moves due to the motion of the shaft, due to the translational motion of the shaft, for example, if it moves to the left here, then more magnetic field will be captured by the coil on the left rather than by the coil on the right. So you will then the difference between this the magnetic field of these two will not be there is some difference, so it will not be zero anymore. Yeah, the subtraction. So like this. This is a type of this sensor is called as LVDT, which is an abbreviation of linear variable differential transformer. Yeah, it is a differential transformer. LV stands for linear variable because it converts the linear motions of the core at the middle into voltage change with the help of the primary and secondary two coil. Okay, so when it is exactly at the middle, when the shaft is centered like this, V1 is the voltage measured by the secondary one coil looks like this, negative sinusoid function. Then secondary 2 will capture a positive sinusoid function like this. The difference between V1 and V2 will be 0. Right? V1 plus V2 equals to 0. Okay, because they are the same, but they only have different polarity. And on the other hand, if the shaft here moves to the left, translationally, what will happen is you have larger V1 compared to the normal condition here. So here you have larger V1. The shape of the wave is still the same, only now you have larger amplitude. But on the secondary 2 coil, it is the opposite that will happen. It will have smaller amplitude. So as a result, then the net voltage between secondary 1 and secondary 2 will look like V1, because V1 here has a higher amplitude compared to V2. On the other hand, if the shaft moves to the right, so more of the core is in the area between primary and secondary, so we will see increase of the signal of V2 and decrease on the signal of V1. Yeah, as a result, the net voltage will look similar to V2 voltage, as V2 here is subtracted by V1. Okay, there is some video. I hope now we have enough volume. Yeah. Okay.
Explain the construction and working of LVDT. LVDT is also known as Linear Variable Differential Transducer or Transformer. It is a passive transducer which measures displacement. It consists of a primary coil wounded on a hollow cylindrical rod and is connected to the AC source. It also consists of two secondary coils having equal number of turns and is wounded on a hollow cylinder at equal distance on either side of the primary coil. The two secondary coils are connected with each other in series opposition, so that the net induced EMF of the two secondary coils becomes, we see that a movable soft iron core is placed inside a hollow cylinder. Position of this core with respect to the two secondary coils will affect the magnetic coupling between the primary and two secondary coils. Let's now understand how this LVDT works. We see that when an AC source is activated, alternating current starts flowing through the coil, due to which varying magnetic field is produced. Now, when this varying magnetic field interacts with the secondary coil, an EMF is induced in the two secondary coils. We see that initially the core is placed in such a position that equal EMF gets induced in both the coils, due to which the net EMF of the two secondary coils becomes 0. This position of the core is known as null position. Now, if we move the core towards the right, we see that the flux linking with coil S2 becomes greater than the flux linking with coil S1. As a result, the EMF induced in the coil S2 becomes greater than the EMF induced in coil S1, and the net EMF shows a negative value. Similarly, if we move the core towards the left, we see that the flux linking with coil S1 becomes greater than the flux linking with coil S2. As a result, EMF induced in coil S1 becomes greater than the EMF induced in coil S2, and the net EMF shows a positive value. Thus, LVDT uses the magnitude and polarity of the net EMF induced to measure the displacement of its core from the null position.
Okay, so I hope this is easy to understand, understandable enough about it. So then, how do we do the measurement? How can we capture this change of electromotive force, the E, between the different transformer? So we can use this AC bridge and resonance circuit. So in AC bridge, the inductance change is converted into output voltage. the output voltage is further amplified, and then using phase-sensitive detection circuit to detect the phase, and then we can do also further filtering. In resonance circuit, the inductive sensor will become a part of oscillation bridge. And so in this case, then the output of the oscillation bridge is a frequency change. If you have frequency change, then you can put it into counter. Yeah, either you make your own counter circuit, or you can use microprocessor to count the frequency. So this is how it looks like for the AC bridge. Yeah, this is the AC bridge circuit. Yeah, this is AC bridge circuit, and we have the signal stimulus coming here. This is the amplifier, and there is a subtraction circuit. Then we have the Y1 and Y2, which is Y2 is the negative absolute value, negator, and another subtraction circuit, low pass filter here, and absolute value circuit. Each of this block is indicated as different circuit. Here, the absolute value circuit will look like this. So negative, the function is to find the absolute value of a number of the value of a signal. Here, if it is negative, then it only takes the magnitude, not the sign. And this is a follower circuit, basically it functions similar like a buffer. Okay, now in what biomedical applications can we use inductive sensor? An inductive sensor can have a displacement measuring resolution of 0.01 micrometer. Yeah, which is good to measure slight displacement. So 0.01 micrometers is about 10 nanometer. Okay, and it has been used, for example, to measure respiratory activities as RIP, not rest in peace, but respiratory inductance plethysmography. Yeah, plethysmography is a way to measure respiratory measurement, but in this case, it uses inductance. There is other resistance-based plethysmography, but here we use inductance. So quantitative and qualitative non-invasive respiratory measurement can be done using this RIP device. It can be used in both adults and infants. The measurements in this case will be the respiratory rate, okay, how fast or how slow the person breathing, then the tidal volume in the lung, from the lung. So this is the illustration from the paper by Mazeika and Swanson in 2007. It's published in this journal, the Respiratory Inductance Plethysmography. Then, so with this, you can capture the respiratory signal, yeah, which you have learned in the previous early chapters this semester. Okay, so this is how it would look like. So there are kind of belts. Yeah, one is that's why I was asking yesterday to one of the group, why they only put in the belt. In this case, for example, for measuring complete respiratory measurement, two measurements are done. One on the chest expansion and contraction, the other one on the belly expansion and contraction. Then the variation of unit volume, the delta V is calculated as equal to K1 times delta LR plus K2 times delta LA. So delta LR is the output inductance change of the thoracic belt in the chest, surrounding the chest. Delta LA is the output inductance change of the abdominal belt in the stomach, surrounding the stomach. K1 is the volume coefficient for chest, K2 is the volume coefficient of abdomen. So here how the respiratory inductance plethysmography RIP can be used to diagnose apnea. Apnea is a kind of disease that happens when people sleep, that usually is related to snoring, that when the snoring gets worse, that it could block the breathing channel, the breathing tract, something like this. So here in this signal, this is how the signal look like for normal breath. Okay, I think that is all for inductance-based sensor. Are there any questions so far?
Sir,
Yeah.
because we already learned about resistive, capacitive, and inductive, what do you think which is the better uh, sensor?
Yes, it depends. If you ask me, I'm a resistance guy. I I often develop more of resistance based sensor, but each has its own advantages and disadvantages. As we have learned, maybe most of the resistance based sensors do not have high resolution. High resolution is usually in capacitive based sensor. However, the circuit in capacitive based sensor, as you know, is not that easy, right? The circuit, but of course, the capacitance change can be also converted by a secondary transducer into delta voltage change, or frequency change. Inductance change, on the other hand, what to say? Yeah, it is also good, but it relates with the measurement of magnetic field. And when in our surrounding there are many electromagnetic interference coming from uh, electrical appliances, from uh, smartphone or whatever, it may not be the best solution, because then the signal created will be very noisy. Capacitance, on the other hand, are good if you have constant dielectric permittivity. For example, your medium between the electrodes change due to humidity, for example, then you may have noises. Okay.